Part C. In this module, we're going to introduce the dynamic signal-to-noise experiment and illustrate it with two examples. In the dynamic signal-to-noise problem, we still have control factors and noise factors. In addition, we have a special type of control factor called a signal factor. The signal factor is a factor that can be used to adjust the level of the response variable in order to obtain a range of performance on the key quality characteristic. In golf, the club head number is chosen to adjust the distance traveled. While driving, the depression of the gas pedal is used to adjust the speed of the car. The goal of the dynamic problem is to optimize the relationship between the signal factor and the output response. Here, optimized means to make the relationship as linear as possible with minimum deviation from the regression line. The dynamic approach is especially useful early in the product development cycle where we don't know what the ultimate aim is going to be. It is also useful when developing processes that are required to produce a range of possible products. In test development, where the test is expected to perform over a range of possible input samples, the dynamic approach can be used to optimize the measurement system. The design layout of the dynamic experiment starts out just as it did in the static experiment. The control experiment and the noise experiment are designed the same way as before. The noise experiment is repeated for each level of the signal factor and each run of the control factor experiment. Usually 3 levels of the signal factor are examined so that the linearity of the response can be assessed. Here's an illustration of the layout of the dynamic experiment. The control factor experiment is shown as rows in the design, while the noise factor experiments are shown as columns. The repeats of the noise experiments at different signal factor levels are shown as additional columns in the design. This is the usual way to display the experiment, although it may not be the way the data needs to be arranged for analysis. The signal-to-noise metric for the dynamic problem is shown here. Here again, we would calculate the signal-to-noise metric for each row of the control factor experiment. This example comes from Folks and Krevlin, page 97. This is an example from densitometry. There are 4 different densitometers in the control factor experiment, that is, 1 variable at 4 levels. There is 1 noise factor, a reading taken at 2 different points in time. The signal factor is the input image density at the 3 different levels. Here is the layout of the data. The 4 rows contain the 4 levels of the 1 control factor, the 4 densitometers. The 6 columns contain the 2 noise factor levels and the 3 signal factor levels. The analysis requires calculating slope and MSE between the signal factor and the output response for each run of the control factor experiment. Minitab can analyze some kinds of dynamic problems, but for some unknown reason requires at least 2 control factors. With a lot of copying and pasting, or some very clever use of dummy variables, we could trick Minitab into doing the required analysis, but it is pretty simple if you use SAS. First, let's rearrange the data. Here we show the data stacked so that the response variable is all in 1 column, and the columns are added for the noise factor level and the signal factor level. Once the data is stacked, we can use procreg with a by statement to calculate the required statistics. Notice here that we have specified the no-int option on the model statement to indicate that we don't want it to fit an intercept. An output statement is used to create a dataset with the slope and root mean square error. A data step is used to calculate the signal-to-noise ratio, and the results printed with proc print. Densitometer 1 is our clear choice from this analysis. It has the highest signal-to-noise ratio, a slope closest to 1, and the lowest root mean square error. I then pasted the results back into Minitab in order to make these plots. The plots confirm the fact that the first densitometer has a very linear response with low mean square error. The third densitometer has a low mean square error, but a slightly more gentle slope. The first densitometer has a relationship very close to the ideal function. The slope between the signal factor and the response is very nearly linear, with a very small variance over the range of the noise conditions. A more realistic measurement problem might use the densitometer as a noise factor rather than a control factor, and let the settings or the calibration procedures applied to the densitometers be the control factors. With only 1 replication, we have conducted no formal test to verify that these slopes or MSEs, are statistically different from one densitometer to another. In the first example, the application assumed that the regression model between the signal factor and the response was linear, with a zero intercept. We do not have to assume a zero intercept. The reference point proportional approach allows a non-zero intercept. This approach allows the modeler to specify a specific point that the regression model must pass through. Here's some more example data from Minitab. There are 3 control factors, each at 2 levels. There is 1 noise factor at 2 levels and 1 signal factor at 3 levels. Here the data is arranged so that each control factor setting, along with the signal factor settings, are rows of the spreadsheet. The 2 response columns represent the measurement of the 2 noise conditions. Minitab expects the control factors and signal factors to be treated as design variables and the noise factor variation to be stored as separate columns on the spreadsheet. Under the defined custom Taguchi design, we just need to put the control factors in the factor box and the signal factor below in the signal factor section. Next, in the analyzed Taguchi design, we just need to specify the responses that make up the noise factor experiments. We also need to specify the terms in the model like we would in analyzing any experiment. Under options, we specify we are analyzing the dynamic signal-to-noise ratio experiment. Here is where we specify the response reference value and a corresponding signal reference value. In that way, we can specify the point that we want the regression function to pass through. Other options are also available on this page. We can see from these effects plots that the choice of sensor has the biggest effect on slope. Sensor 1 has a higher slope. The choice of sensor also has the biggest effect on the signal-to-noise ratio. Sensor 1 has a higher signal-to-noise ratio. This is the interaction plot for the slopes. From these plots, it appears that there may be an antagonistic interaction between the output and the relay factors on the slope. This is the interaction plot for the signal-to-noise. Interactions are less obvious here, although it looks as though something might be going on between the sensor and output factors. If we fit a model that includes main effects and two-way interactions, it leaves 1 degree of freedom for error. Estimating the model this way results in no statistically significant effects. Of course, there is no true replication and not much power here to detect difference. If we allow the two-way interactions to go into the error mean square, then the sensor factor becomes significant for both signal-to-noise and slope. A normal probability plot would be nice, but as we saw before, Minitab's Taguchi procedure doesn't do that. We can use the storage in Taguchi procedure to output the slopes and signal-to-noise ratios, and then use the factorial procedure to make normal probability plots. Nothing turns out to be statistically significant for the signal-to-noise ratio, although the point that is farthest from the line is the sensor factor. The sensor is identified by Minitab as being significant on the slope. We will want to pick the sensor at the low level, both for the higher signal-to-noise and higher slope. Since the effect of other variables is not as large, we might choose any level. But if there are no other economic considerations, we might as well choose the levels which maximize the signal-to-noise ratio. If we use Minitab to predict the signal-to-noise ratio, slope, standard deviation, and log of standard deviation, we get these values. The predicted values agree reasonably well with the actual values observed in the experiment. In this example, we would choose the sensor at the lower level in order to maximize the signal-to-noise ratio. The sensor at this level also results in a slope that is closer to 1. Other factors can be chosen to minimize cost, or in the absence of economic considerations, to maximize the signal-to-noise ratio. Verification runs should be made at the optimum to validate the final choices of the control factor setting.